Welcome to this explainer. Today, we're diving into something literally mind-boggling. We're going to explore exactly how the universe baked its very first ingredients out of a hot, dense soup, all within the first 3 minutes of existence. It's a story of, incredible heat, absolutely perfect timing, and a cosmic recipe that set the stage for basically everything we see today. Let's get right into it.
So, where did the atoms in your body actually come from? We're talking about the carbon in your DNA, the oxygen in your lungs, the iron in your blood. It's totally fascinating to ponder. But I'm going to tease a little twist right up front here. While our bodies are constructed of these beautifully complex elements, the early universe, well, it really only provided the initial fuel.
To really understand how that initial fuel was made, we kind of need to think of the early universe as a giant cosmic kitchen. And notice how incredibly short this window is. We start with the Big Bang at 0 seconds. Bam! Then we hit a crucial milestone at just 1 second. Actual fusion, that begins at 3 minutes. And then, amazingly, the oven shuts off entirely at just 20 minutes. That's the whole shebang.
Section 1. The cooling cosmic kitchen.
Okay, first off, we have to clear up a common misconception. The early universe wasn't just, vast empty space. Actually, it was this high-energy, incredibly violent soup of particles. At the Big Bang, which is the beginning of our observable universe, it was extremely hot, super dense, and expanding rapidly. Atoms couldn't even exist yet. It was just way too hot. I mean, the universe had the raw ingredients for sure, protons and neutrons, but they were zipping around way too fast to stick together. Anytime a fragile little nucleus tried to form, these highly energetic packets of light called photons would just violently blast it apart.
Moving on to Section 2, the frozen ratio.
So, because the universe is expanding, it's also rapidly cooling down. And right around that crucial 1 second mark, the universe essentially locks in its base ingredient list with a highly specific ratio, 1 to 7. That's about 1 neutron for every 7 protons. Now you might be wondering, why that exact number? Well, it's because neutrons are actually slightly heavier than protons. So as the universe cooled, the reactions that were bouncing back and forth, changing neutrons into protons and protons back into neutrons, they just became too sluggish. The imbalance totally froze right exactly at that 1 to 7 mark.
And this seemingly simple 1 to 7 ratio, it's absolutely crucial. It completely determines our cosmic recipe. Think about it. Because we have far fewer neutrons, and because most of those limited neutrons are going to quickly get locked up to form helium, the vast majority of those extra protons are just left hanging without a partner. And what is a solo proton? It's simply a hydrogen nucleus. So this frozen ratio is literally the exact reason why our universe ended up completely, utterly dominated by hydrogen.
Section 3. The Deuterium Bottleneck. But wait, we aren't quite ready to bake yet. The universe really wants to fuse elements together, but it hits this subatomic traffic jam. To build helium, you first have to make a stepping stone element called deuterium. That's just 1 proton and 1 neutron fused together. But here's the catch. Deuterium is incredibly fragile. Before the 3-minute mark, it's still way too hot. Deuterium tries to form, but those energetic photons instantly smash it apart. But then, after 3 minutes, the universe finally cools down just enough. The photons lose their punch, the fragile deuterium survives, and boom, the bottleneck clears.
Which brings us to Section 4, building the cosmic recipe.
With that traffic jam completely cleared, the universe has cooled to the perfect baking temperature. Rapid element fusion can officially begin. And let me tell you, it happens incredibly fast. Step 1, a proton and a neutron lock together to form our now surviving deuterium. Step 2, another piece gets slapped on there to create helium-3. Step 3, we arrive at the highly stable helium-4, which has 2 protons and 2 neutrons. And because helium-4 is so stable, it's like a magnet. Almost every single available neutron in the entire universe gets rapidly sucked up and locked into these helium nuclei.
And the result of all that rapid fusion, it's this incredible final cosmic recipe. If you take that initial 1 to 7 ratio we talked about, and you pair up the neutrons to make helium-4, you end up with exactly this distribution by mass. Roughly 75% hydrogen and 25% helium. Remember those extra protons we mentioned? The ones that just couldn't find a neutron partner? Yep, they simply stayed as hydrogen.
Now, obviously, hydrogen and helium make up the massive, overwhelming bulk of the universe here. But it's definitely worth noting that tiny trace amounts of other light elements did manage to form during this incredibly chaotic window. We're talking about less than 1% by mass in total, and that mostly consists of leftover deuterium, some helium-3, and just a tiny bit of lithium-7.
Okay, Section 5, why the baking stopped.
So the cosmic oven is cooking, right? We've got hydrogen, we've got helium, but
Why didn't the early universe just keep going? Why didn't it keep fusing heavier elements? Where's all the carbon, the oxygen, the iron we need? Well, the answer is this really dramatic twist of physics. The universe basically hit a brick wall in the form of mass gaps. Turns out there's no stable nucleus with a mass number of 5, and no stable nucleus with a mass number of 8. So when the universe tried to climb the fusion ladder past helium-4, the very next steps literally fell apart instantly. Try to add a proton to helium-4 to get a mass of 5, it breaks down. Try to smash 2 helium-4s together to get mass 8, it breaks down. The fusion ladder was completely broken.
And because it was stuck at that broken ladder, the universe just plain ran out of time. By the 20-minute mark, the universe had continued to expand, and as a result, it cooled and thinned out dramatically. Now, just to be totally clear, when I say cool here, I still mean roughly 1 billion degrees. But in cosmic terms, the oven was off. It became way too thin for Big Bang fusion to continue. The cosmic kitchen definitively shut down.
I absolutely love this quote because it really grounds everything we've just talked about. The Big Bang gave the universe fuel. It did not give us the main bricks of life. The Big Bang was a masterful baker of hydrogen and helium fuel, for sure. But it completely lacked the time, the pressure, and the stepping stones to build those heavy elements. It really sets up the need for a completely different kind of cosmic kitchen later on down the line.
Section 6. Evidence in the afterglow. Now, it is totally fair to ask, how do we actually have proof of a 20-minute baking session that happened over 13 billion years ago? Well, we rely on 3 main pillars of observable evidence. First up is helium abundance. When we look out into the universe today, the amount of helium we actually measure matches that mathematically predicted 24 to 25% perfectly. Second, we have those light element traces. The observed amounts of those tiny trace elements, like the deuterium and lithium we talked about, they broadly match all our nucleosynthesis calculations. And finally, the cosmic microwave background. This is the literal, faint, observable afterglow of that hot, dense early universe radiating throughout all of space. The physical evidence just matches the theory so beautifully. So we're going to wrap up with this ultimate thought-provoking question. If the Big Bang only made hydrogen and helium fuel, where did the carbon in your body actually come from? Where did the iron in your blood come from? The first 3 minutes gave the universe its foundation, absolutely. But to forge the complex bricks of life, the universe eventually had to light up a whole new set of ovens, the stars. But exactly how stars did that is a topic for a whole other explainer. Thank you so much for exploring the early universe with me today.